So welcome back, campers. So I haven't heard very many questions from you about the homework that is due on Monday. So that either means that it's not going very far yet, or it's already gone. Would anyone like to ask me any questions while I have this pulled up? Not yet?
So we have to do centering, right? So
Yes.
Like it says like a centering at 4 something.
Yes. Yeah, so there's two continuous predictors. One is enthusiasm, which you can leave uncentered because the mean is already near 0, and experience you're supposed to center at 4.
Yeah, at 4, right? Because when I was like doing assignment, originally I thought like I have to center at 4. So like let's say I don't exactly remember what was mean, but like my original mean was like 4.5, for example. So originally I tried to do the subtract 0.5.
Oh, yeah,
It's
no.
wrong way, actually, right?
Yeah, just -4. That's
minus
all.
4.
Just -4. Yes.
It's a reason, yeah.
Yes, and I did not require a centering rule for group because there's no questions that would change based on that, the way I worded it. So you can choose to code group on your own via 3 contrast, or you can let it be an IDOT variable or a class variable and have the program do it for you, your choice. So.
What's a free S? Before free S, it can be English question. Before, I mean, the group before free S is the base. What's
Oh,
free S?
a versus. Yeah, so there are several questions like this one. Fixed effective control versus mini golf. So in the estimate statement, the one that is before gets the -1 and the one that's after gets the 1. Otherwise, the answer will still be correct, but it will be exactly backwards in sign relative to what's here.
So you said you have, when you compare something and control, like you still need a -1 to control as well?
It depends on where you're getting the information from. So if you set it up in the model such that control is the reference group, and you get a comparison of each other group as a model parameter, those will be in the right direction. If you have to ask for it as a model implied difference, then you have to make sure the direction is such that control gets the -1 and the other group gets the 1. And the same is true for these other comparisons that don't involve control. The one that's listed first gets the -1.
Because actually when I did I think I misunderstood the linear combination one. So I thought when we compare control and something else, let's say mini golf, I thought control should be just multiplied 0, and mini golf is multiplied by 1. And then I think actually, but still my answer for the imputation part said it's correct. So
You'll have to. If it's correct, then good. But if it's incorrect, check the direction. So you may have something that is the right answer, but in the opposite direction. So put a minus in front of it or take it away is the difference. By the way, the example that I would recommend to follow to help you with this one is 2C, the middle one. This one in example 2C, I have treated one of the interacting variables as continuous and the other as categorical. That will map most directly onto what we're doing here. Or you can do all the contrasts yourself, your choice. So, all right. Other questions?
I have a question.
Yeah.
You say use 4 as a centering point and use 0 as a centering point. But I'm obviously not subtracting 0, right? It doesn't do anything when I'm centering. So what am I subtracting?
Nothing. You can use the original variable.
Okay, that's what I thought, but
Yeah. Yeah, leave it uncentered would be another way of saying that, but I was being literal. Yeah. So yes, one of my shorter assignments, only 35 answers to enter and 66 total questions. I think my personal best is 110, so we got a ways to go before I hit that. But the good news is that if you get stuck on anything, each question is worth just a tiny fraction of a point because there's so many, so no stressing. Let me know if you run into problems. It's okay to send me snippets of code in an email and say, why isn't this working? Or I think this is what it should be and why is this not running? I can help you troubleshoot things if you run into them. So this is due Monday night at 11:59 p.m. All right. Any other questions? All right, then I will shut this down and we'll go back to the main story here. So let's do a little bit of review. So I started with this slide last time, level 1 predictors, and I have a caveat here that this is likely to be very, very, very wrong. Why am I so emphatic that this is going to be wrong? What's the problem here? So I'm taking a level 1 predictor, entering it into the level 1 model, and giving it a fixed effect. What's the problem?
It probably has like a level 2 effect to the schools vary by how much the kids read.
Yes, it probably has a level 2 effect if the schools vary by how much their students read. How can I find out if the schools vary by how much their student read? Intraclass correlation from an empty model pretending reading is an outcome. If you have level 2 variance in the level 1 predictor, your ICC will be greater than 0. If you have level 1 variance, your ICC should be anything less than 1. So some number between 0 and 1 means that what you're thinking of as a level 1 predictor is actually a level 2 predictor also in terms of the information it contains, and therefore its effect needs to be separate at each level of the model. So this problem, what is my name for this fixed effect that you get from incorrectly estimating this model? This is the smushed effect, yes. And if you don't want to say smushed in a publication, what else might you call it? Convergence, conflated, composite's another one, but I don't like that one as much. Conflated would be my second choice. But I am trying to make smushed happen, so feel free to use that. I defined it in a textbook, so therefore now it's a thing. So we talked about one method in how to fix it, which is to do group mean centering, which looks like this. So we take our original predictor variable at level 1 and we create 2 new predictors out of it. The level 1 variable is your original level 1 predictor minus the group's mean. So this is a very special kind of centering because you're not centering at a constant, you're centering at a variable. You are removing the level 2 variation from this level 1 predictor. So what's left? The within group, X as I call it here, is only level 1, only within groups. You know then for sure that it can only be the level 1 effect in your model. That information about differences in groups in their means, say for reading in this case, is not lost. It goes into the level 2 model as a predictor, centered at a constant so that 0 means something. So Emily, you had questions about this. What constant you pick does not matter. Any constant is as good as the next. Pick something in the middle. The only thing that you're worried about is making sure that you pick something to where this new predictor's, when it's 0, it means something. That way your intercept means something. And if you have interaction terms, the main effects of the interacting variables mean something. But any constant is as good as the next. So
I think the constant only change the random intercept, or it doesn't matter, because did you compare, for example, like a group 2 mean-centered variable, and then without the constant, and then with constant. So
if
they
you
change only the intercept?
the fixed intercept is what it will change, yes. In a main effects model, it will only change the fixed intercept. If this new variable is part of an interaction term, it will also change the main effect of the interacting variable, because the main effect will be specific to when this variable is 0, and so picking a different constant picks a different 0. But in terms of the model fit, the quality of the model predictions, variance accounted for, none of that matters as a function of constant. So the centering that we're doing at level 1 is very, very different. It matters. You end up with very different answers whether or not you do a group mean center or you pick a constant here. The other way of setting up this model puts a constant here, and that's difference, whether you're centering in a variable and removing information, or whether you're just rescaling with the constant. That's the big difference to keep in mind. So then when we put those in the model, each has its own effect at its own level. So we have the level 2 effect is a between level effect. So it's the effect of being from a group that has more of the predictor on average. If so, it should explain your level 2 random intercept variance. The level 1 effect, the gamma 1O here, is the effect of being a person who has more of the predictor than the rest of your group. If that matters, it should explain level 1 residual variance. Okay, questions on that? All right, so we looked at an example. We're still in example 3A. Let's pick up where we left off, thereabouts. We were looking at the effects of IQ. So we did intraclass correlations for each of the student level IQ variables. There's verbal and there's performance. We found that 12% of the variability in student verbal IQ actually has to do with school mean differences. And we found that about 5% of the variability in student performance IQ has to do with school mean differences. We then fit a model where we included both level 2 and level 1 effects of verbal IQ simultaneously. So school mean IQ verbal is the school means, and I put a 0 at the end here just to remind you that I've centered it at 0, meaning I left it uncentered. I did that because IQ is a z-scored variable to begin with, so 0 should be near the mean. Within school IQ is each student's IQ minus their school's mean. So this is the pure level 1 variable that goes in there. And we talked about the results last time, I believe, and looked at the effect size for each of those. So any of that you want to review before we move on to the next model? No? All right, let's do it again, but swap out performance IQ. So we know that verbal IQ matters. It's predicting language, so that's not a big surprise. Let's see if performance IQ matters. So I'm starting with model 3B on page 14. First things first, always the equation. So I have picked up in the level 1 model a new beta 2. This is how each group is going to get its own slope for the within school effective IQ. So each student's performance IQ minus its school mean. That's the variable that's going in here. So it's a pure level 1 predictor. Because I have a new beta 2 in the level 1 model, I have a new equation for it in the level 2 model. So 3 level 1 betas translates into 3 level 2 beta equations. Because it is the equation for beta 2, every term in here is going to start with a 2, and it's the first term is the fixed effect, that's the 0. So we're just adding a fixed effect for now. Likewise, here for IQ performance, I'm adding the school's mean as a level 2 effect. So those new variables show up on the list of predictors. In neither program do you have to denote them as level 2 variables or level 1 variables. It figures it out. I'm asking for several additional pieces of information in each of my programs here. So contrast in SAS and test in Stata, these are used to create a combined test, a multivariate wald test, for the overall effective IQ across levels for each type of predictor. So does verbal IQ matter is answered by 2 different fixed effects. I'm asking, is that combination of fixed effects significant? Likewise, does performance IQ matter is a question answered by 2 different fixed effects. I'm asking for a test to put them together to test simultaneously if they're different than 0. And last but not least, just as another example of something that you might want to do someday, You can answer questions about the relative importance of predictors by comparing their fixed effects. So I put these on z-score scales in total so that they would be comparable. If I wanted to z-score them per level, I could have done that to make them absolutely the same, but given that they're on the same metric of what a z-score means, it's pretty close. So I'm asking for a comparison of whether the effect of school verbal IQ is different than the effect of school performance IQ, and doing the same thing at level 1. So just as an example of something you might be interested in, if you have predictors that are on the same scale, you can ask for comparisons of their effects as well as other types of linear combinations. So survey says, here's my 2 new fixed effects. So school mean performance IQ, is that a level 2 fixed effect or level 1? School mean performance IQ. It's 2. Yes, so fixed effects can be at either level. There were a few answers on your quizzes that had confused that fixed effects are not, in the equation, they are shown at level 2, but with the variable that they eventually refer to can be a level 1 variable or a level 2 variable. So the first one then is 2. Would someone like to put the 2 in a sentence for me? See, if I had candy, I'd throw it at you. Or maybe I should bring money instead. That might be more motivating.
Is it for every point increase in,
School mean performance IQ.
yeah, in school, then what the outcome is? What's the outcome?
Language.
Then language increases by 2.8?
Mm-hmm. So the inference is that it's not just language, but it's language for your whole school. Like it's a bump for everybody because this is a school level effect. So then the other one within school, who'd like to do this one? What do you think? Way, right?
Yeah. For every increase in within school IQ performance score,
Mm-hmm.
you get 1 unit increase for all the kids in the same school.
So for every unit higher within school IQ, so translates that's unit higher than other people in your school. So if you're relatively smarter, for every unit relatively smarter you are, your language, not your school's, yours, goes up by 1.6. And the effects of verbal are still uniquely significant, although a little bit smaller, after controlling for performance IQ. So in writing up these things, it's really important to specify what the relative comparison is, like 1 unit higher school mean versus 1 unit than the rest of your school. So if you get used to using those sorts of terms, you can help identify and describe why you have 2 different effects of the same predictor in your model. So what if reviewer 3 looks at what you've done here and says, wait a minute, you have verbal IQ in here twice? That's bad because like collinearity and stuff, and why'd you do that? What? Yeah, because collinearity and p-hacking and bad and missing not at random too. Just throw all the complaints in there. But let's say you have to answer to reviewer 3 who's confused as to why you essentially have what they think is the same predictor in here twice. Dear reviewer 3, right? First thing, always, what do we start with? Those of you who had me before know the answer. What? That's a good one. Thank you for your careful read. That's a good one. We apologize for not being sufficiently clear, because it is your fault that they didn't understand what you did. As now explained more clearly on page 14, ... What's my response?
You put Lisa Hoffman reference book.
Yes, personal communication. Lisa said to. No, they're not going to buy that. Well, you could say, though, according to Hoffman 2015, because that is not a personal communication. That's me personally communicating to my book, which someone could buy, and that somehow makes it better. But no. What's the logic beyond just Lisa said so? Is there a problem that I have the same, what looks like the same predictor in here twice? Let's tackle that.
So we were just talking about how it varies for both levels.
Yeah. So is this the same predictor? Are these predictor variables related? They're not related at all. That's what group mean centering does. It renders them completely orthogonal. Within school IQ is the difference between your score and your school's mean, whatever that is. What the mean is, differences in the school means, is captured by the level 2 predictor. So why is it that some schools have smarter kids? Well, I don't know. There's a lot of reasons for that. Why is it that some kids are smarter than others, even though they go to the same school? Different reasons for that. So theoretically different variables. And if I had put just one of them in the model, that would be the cardinal sin of smushing. And the way I would explain that is that a single predictor would force the level 2 between school effect to be equal to the level 1 within school effect. And I can actually answer the question as to whether or not that's okay. I already have this down here as a contextual effect. So we'll talk about what that means later on, but you can think of it for now as the straight difference between these numbers. I have an estimate statement to ask me if they're different. For verbal IQ, the answer is yes. For performance IQ, the answer happens to be no, but for right now. So, yeah.
What of them were not significant? Would you remove it from the model, or you will keep it?
In this setup, technically speaking, there's nothing wrong with removing something, either of these, if they were non-significant. I think of them asymmetrically, though, in how weird that would be. So, for instance, let's say that within school was not significant. I would have no problem with removing it and leaving only between school differences in the level 2 model. The opposite, though, if between school is not significant, but within school is significant, I would feel weird about getting rid of between school. Because what this within school variable means is how much smarter you are than the rest of your school. And if the rest of your school isn't in the model, then like smarter relative to a reference point that's missing, it makes me feel squishy. It's weird. So I wouldn't, because then it becomes like a weird interpretation. But that's my personal preference.
If they are significant, then does that mean that you don't have that thing where it can vary in both levels?
If they're not significant, it doesn't mean that they don't vary at both levels. So having variance, say, in IQ at both levels, we know that because the first thing that we did with those variables is estimate an empty model for them and get the intraclass correlations. So we know, for instance, that 12% of verbal and 5% of performance is level 2 variance. So that is a logical prerequisite for that variability to predict something else. But just because that variability in level 2 doesn't predict a level 2 outcome doesn't mean there's no level 2 variability. It's two different things.
So what does it mean if it isn't significant? Like, how would we interpret that?
If it weren't significant, it would mean that schools that have higher mean IQ do not have higher mean language. I mean, it's just a zero effect, the same as I tend to put the direction in there when I talk about things. So I'd say, non-significantly higher or non-significantly lower, but it would mean the same thing as any other regression slope. you just have to keep the level of inference. The school mean effects are talking about what happens to the whole school's outcome as a function of this school level predictor. The within school effects are talking about what happens to that kid's outcome as a function of that kid's predictor. Okay, other questions? What about interaction terms? You knew I was going to go there, right? You knew I was going to. That's the last model, I believe. Because it's reasonable to think that two different measures of IQ at some point would trade off, right? At some point, you would think that having more IQ of each kind doesn't help anymore, right? You're already brilliant. Being brilliant in another dimension isn't going to help your language as much. So that idea of diminishing returns motivated the last model here. So I am doing level-specific interaction terms. So at level 1, I have added interaction between the within school verbal IQ and the within school performance IQ as a new beta 3. Because I have a new beta 3 in my level 1 model, I have a new beta 3 equation in my level 2 model. It starts with 3, and it's the first term, so the second subscript is 0. And likewise, I have gamma 07 right here for the school mean IQ verbal times school mean IQ performance. So gamma 7, this is a level 2 equation, or interaction, excuse me, in the level 2 equation. Gamma 30 is a level 1 interaction. Could I have put a school variable interacting with a within school variable? Yes, but not yet. Because I would have to do something else first that we haven't talked about yet before I tested that one. So put a pin in that one for now. So as I am prone to do, I wanted to try and describe these interaction terms at each level using the same techniques we went over in regular linear models for single level data, asking for simple slopes at representative values of the other predictors, as well as regions of significance. So I have a contrast for whether or not the two new interaction terms as a set improve the model. I have asked for COV-B, which is the asymptotic covariance matrix of the fixed effects. That has extra things in it you need for the regions formula. And I am saving that covariance matrix, the solution for fixed effects, and the covariance parameters to data sets so that I can then do the math on them to get the regions of significance. Otherwise, the estimate statements to get the simple slopes look exactly like what you're now very used to seeing. Whatever variable you want the slope for gets a 1, and then you fill in the value of the moderating variable for which the simple slope should apply. So for instance, this line right here, that is asking for the predicted school level effect of performance IQ at a relatively low verbal school. So I have low, medium, high at level 2, and low, medium, high. So in this analysis, I'm treating performance IQ as the variable I'm interested in and using verbal IQ as the moderator. So, questions on that setup? All right, let's see what happened. So I rearranged this output so that it would be easier to talk through and talk about the interactions. So I took some liberties with the order. But yes, overall, we did account for significant variance with the two interaction terms. Now that this is the last model I'm fitting to these data, I wanted to go back and calculate an intraclass correlation and a design effect. So this is what's known as a conditional intraclass correlation. It is the proportion of group variance that remains relative to the total variance that remains. So our original intraclass correlation for this language outcome was 0.23. It's down to 0.16. How could that happen? Because we were relatively more successful in explaining level 2 between group random intercept variation than we were successful in explaining level 1 within group residual variation. So the total pseudo R-square relative to the empty model I gave right here. So of the original 23% that was level 2 school variance, we got 61% of it with our school level predictors. Of the original variation at the level 1 student level, that is 77%, we got 39% of that. So we did better at level 2 than we did at level 1. The conditional intraclass correlation is lower than the unconditional. What that translates to is less of a problem of our cluster data, a smaller design effect. So if I use the average number of students per school minus 1 times my new conditional intraclass correlation, add 1 to that, I end up with a design effect that's 3.7. An effective sample size of my actual sample size divided by that design effect works out to be 893. So according to the empty model, we had an effective sample size of 677. Because we've reduced the dependency of schools, because we have reduced the relative amount of information that is level 2 school mean differences, it's like we have more people. They're less like each other. So we went up to 893. It doesn't mean that we can go back to single level regression, but we're heading in the right direction if our goal was to explain level 2 school variance. Okay. Any of that you need to hear again or have questions about?
So do you always expect the ICC to be lower, or because on the
Nope.
other hand, according to you, the MLM should be up?
Yeah, if your level 1 model is better than the level 2 model, then your ICC will go up after including predictors, yeah.
But it's the opposite, disagree with
It would be more of a problem to ignore the dependency due to clustering in that case. But if you're doing the modeling correctly, you would never have a situation where you ignore the dependency no matter how small it gets. Other questions? All right, so that's effect size. Let's see what happened. Improvement in total R-square of about 0.4%, so our interactions are not huge, but let's find out if they are worth talking about, and indeed they are. Time to play everyone's favorite game. More positive, less positive, more negative, less negative. Woo! See, that one sounded sarcastic, Molly.
Sorry, not caffeinated enough.
Yeah, I hear that. Let's all pause and reload. Yes, Mountain Dew, of course, one of the higher caffeine sodas that you can consume. Yeah, I think this is like 70-some grams of caffeine per can. Yeah, well, when you got to talk for 3 hours straight, you can't do that unaided. I have to tell you, one time I gave a 4-day workshop at Brigham Young University. That campus has a lot of predominantly Mormon students and faculty. They don't believe in caffeine. And I made the person that drove me stop at a convenience store, and I snuck in Mountain Dew as contraband. So I can't talk for 8 hours with no caffeine. That's just bad. Yes, and then I had to work really hard those 4 days not to say shit and stuff too, which was also problematic. But, you know, the things that we do for love, the love of the game, so to speak. So what I want to know is, does more IQ help, or are there diminishing returns? That's my question. So let's take these interaction terms where performance IQ is the thing that I care about, verbal IQ is my moderator. Okay. So this school mean performance IQ, that is conditional on schools that have average verbal IQ of 0 In those schools, for every unit higher school mean performance IQ, your school language goes up by 2.8. Significant. What happens to that school level performance IQ effect in higher verbal schools? It becomes less positive, which means stronger or weaker? Weaker, yeah, diminishing returns. So yeah, if you're also from a school with high verbal IQ, having higher performance IQ starts to matter less. At what point does it not matter? Wouldn't that be nice to know? Can you think of any way that we could figure that out? Yeah, I accept gestures. Yeah, I know what you're doing, right? Like regions? Yeah, regions of significance. We can do that. How about this one? Within schools, if you have average verbal intelligence relative to the rest of the peers in your school, for every unit more performance IQ you have than others in your school, your language goes up by 1.6. What happens to that effect in kids with higher verbal relative to their school? Less positive, it's weaker. At what point does it not matter? Wouldn't that be nice to know? So let's find out. So here are the simple slopes. These are examples of how the level 2 IQ performance effect changes across level 2 verbal IQ. It's positive in relatively low verbal schools, less positive as you increase, and at some point it shuts off. Shuts off meaning is non-significantly positive. So based on these 2 points, I know it happens somewhere between a z of 0 and a z of 1. Level 1, here are my simple slopes. Same pattern, but less pronounced. So having higher performance IQ helps more if you have low verbal, helps a little bit less as your verbal increases, but it always helps according to these 3 simple slopes. So the point at which it doesn't help anymore, the slope is not positive and significant, we don't know. So that's where regions comes in. So the idea of regions of significance is taking the t-test for when you would pass, the t would pass that critical threshold for significance, and working backwards to figure out the slope at that point. So I have an Excel spreadsheet that I built that you can download as part of Chapter 2's materials from my books, and I think Chapter 7 I did it, and I also built a SAS macro that does this. So it takes as input the arguments, the fixed effects from the model, the asymptotic covariance matrix of the fixed effects, which has the standard errors and the covariances of the standard errors. It wants to know which is your predictor and which is your moderator, the centering point of the moderator, and the order of the interaction term in your model. And it worked out to be this. So,
I've got one question.
Yeah.
Like, for the moderation effect for the performance IQ on the verbal IQ, we see like in level 1 and level 2, they are in the same direction, like all becoming less positive.
yes.
But is it, can we see like the opposite
Yeah.
between level 1 and level 2? Like one stronger and the other is weaker?
It depends on the direction, yeah.
Okay,
So if a
not
main
always like the same direction.
Not always, no. So if you start with a main effect that is positive and you have an interaction that's negative, it makes that main effect less positive. If you start with a main effect that's negative and the interaction is negative, it makes that main effect more negative, which is stronger.
Okay.
So you don't know which it is unless you have a main effect to go off as a reference point. But yeah, you could absolutely have that. If you had one predictor that helped and one predictor that hurted, the interaction term could make one stronger and the other weaker at the same time.
What does water you mean?
What does what?
What order? Because the previous one was 9 and that was 10.
Oh, that is because I'm a lazy programmer. It's literally the order that it's written here. That's just make it easy to go find that entry and save it. Yeah, I don't like sell my macros, right? There's a reason. It's a buyer beware. But I make them work well enough within the confounds of my programming ability. So what does this mean? I have a lower bound of 0.38 and an upper bound of 6. So I have it written out here because it usually takes me a minute. The school level effective performance IQ will be significantly positive for school mean verbal greater than 0.38. So that corresponds to this. We just figured out that z of 0.38 is where we hit the point where this positive slope is no longer statistically significant. Now, this number getting less and less positive, it's eventually going to flip, right? As it gets smaller and smaller, it's going to head negative and become more and more negative. And the interaction predicts that at some point that the slope will be significantly negative if I go high enough on z. The point at which the slope becomes significantly negative corresponds to a z of 6. In this case, I don't have any schools with the z of 6. So the inference is that about half of my schools, z-score greater than or equal to 0.38, they're going to have a significant effect of performance IQ. For the other half, once you get enough verbal IQ, the effective performance IQ doesn't matter.
Can I ask a question?
Please.
So you start with a T, but to do that area you go into C. Yes?
You go into C? Is that what you said?
Yeah, C. You start with a T test.
Yes. Let me find.
But to find that region, you move into a C distribution.
I'll show you where it is. It's right here. So it starts with this basic formula, and it rearranges it to figure out what the slope estimate must be to hit t at plus or minus 1.96.
So when you're doing this, you don't worry anymore about the T distribution.
Nope, I'm just using it as a benchmark.
Okay, because my other question was going to be, I noticed that your degrees of freedom changed.
Mm-hmm.
So I was wondering which degrees of freedom you pick. The answer is none.
Correct.
Okay.
Yeah, this, in chapter 2 of my book, I give some of the original references for this. The formula is kind of ugly, but I mean, this is the concept, basically. It's trying to figure out at what point things, according to the model, you know, where the changes stops being positive and where it heads negative.
It's pretty cool. I'm not sure if I ever been exposed to this before. If I have, I forgot.
Well, I think when you have two quantitative variables that interact, this makes more sense than picking arbitrary points to get slopes at. If the story were different here, like if the interaction was between IQ and like something that's binary, then I would just get the IQ effect for a 0 group, the IQ effect for the 1 group, and be done. But in this case, there's like an infinite number of groups so this makes more sense.
Cool.
Yeah, sure. So yeah, so for about half the schools, performance IQ matters, but once you get high enough on verbal, it doesn't matter significantly anymore. Yeah.
I have a question about the critical region. So I understand when you have two lines like this,
Mm-hmm.
they can go from significant to non-significant to significant.
Mm-hmm.
But how is that gonna happen when you start to have significant? And it's like
they're going away and then they eventually meet again.
Yeah, so let me get out my favorite tool, Paint, here. There's my axis. So this is school mean performance IQ. It's hard to write with a mouse, so we'll do this. Performance IQ. There's a positive effect where more helps. The pattern of the interaction is that as Z increases, it helps less, right? So where the line becomes functionally flat is Z of 0.38. So this would be like Z of -1 or so, and it keeps going, right? So if you follow what the linear model says is going to happen, for every unit, this slope 2.8 becomes less positive by this, it heads negative. So 2 units is gonna, 1 unit reduces it to almost 0, 2 units heads it into negative territory. So it keeps going, like eventually, if you go far enough, right, it's gonna hit negative. So the regions is trying to figure out where the positive transitions to 0 and where 0 transitions to negative. And where the transition is to negative is a Z of 6, which we don't even have. So there's no schools for which more IQ is a bad thing. Okay. The other one, moderation, it looks to be a little bit weaker in terms of the coefficient. And so I did levels of regions of significance for that, and found that so long as you have a Z less than 3, so if your verbal Z is less than 3, your performance slope is significantly positive. So if I go back to my picture here, same idea, where the cut point is 3, from 3 up to 34, it's non-significant, and it's bad for you after a Z of 34. Have you ever seen a Z of 34? 34 standard deviation seems like a bit extreme to me. So yeah, I think it's safe to say that having more performance IQ is still helpful to some extent. It's just less helpful if you already have good verbal IQ. Diminishing returns. An under-additive interaction. And, as promised, words. So what I didn't make is a picture. It would be nice to illustrate the simple slopes would be something along these lines, but maybe not in Paint. You know, at least put it in Excel if you're not willing to make a fancy graph, but something to convey the idea that you have different slopes for different folks, different slopes for different schools would be helpful.
Simple slopes are connected to simple effects.
Simple slopes are simple effects.
Thank you. Now they're
Yeah.
working together.
Yeah, this idea of picking arbitrary points on the moderator and finding the slope, that's known as probing the interaction to certain people. That word just makes me, like, there's nothing good that comes from a probe, right? Like, that's just, so I just think of that as, these are predicted simple slopes. The model tells you what it should be for any variable. The ones you get by default is the one for Z equals 0. But you can get any other one that you want. All right, and words. Okay, how are we doing? Good. So after class, Dr. Aloe, Ariel to his friends, asked me a question. I think it was during class, we talked about after class. What if my level 1 predictor were binary? So what if you go back to this idea here of group mean centering that we've just now thoroughly explored. So pros to this approach, it's simple. You put in the hard work to set up the variables, and once you have these variables, you have to know what they mean. The group mean only has level 2 variance. It can only have the between group effect. The within group deviation from the group mean only has level 1 variation. It can only have a within group effect, the end. So I like it because it's hard to screw up. Now what if my level 1 variable here that I were doing instead was something binary? So what if reading was measured whether or not you read to your child last night? Yes or no? Do I want to group mean center this? Now I could. Like I could calculate the proportion of students who were read to last night, and that proportion would range from 0 to 1. And I could take my value and subtract that school's proportion, and I'd end up with like a decimal, right? I'd end up with like a 0.3 or a 0.7 or something like that. Now there's nothing wrong with that, but it's weird because 0.3 and 0.7 aren't logically possible values. And it gets weirder when you put them in an interaction term where the interaction term, the main effect is conditional on that value that can't happen. So then the question is, well, if you have a binary predictor, is this okay still? Nope. But in that case, you want to do something different. Which is not, which is, ... wait for it, not do group mean centering. Leave it alone. But don't smush. So what we're talking about is, starting on slide 38 here, this is what I would do if I have a binary level 1 predictor, or in a few other cases. We'll talk about those in just a minute, but let me present what the strategy is. Don't use group mean centering. Take your level 1 predictor and either center it at a constant so that 0 means something, or leave it alone. If I have a binary 0, 1 variable, I leave it alone. I put in binary reading as a level 1 predictor. But I also still put in the group's mean. How? Because I make a group mean and I put it in the level 2 model. Now, this is going to blow your minds. I'm just going to put it out there. This is a really hard concept to explain, but I'm going to try. Everything changes at level 2 when you do it this way. Why? Because let's think about what is happening behind the scenes. So do you remember regression, right? Our old friend single level regression, and you talked about the idea of unique effects versus bivariate effects, right? So if I have two predictors that are uncorrelated, like x1 and x2 here, assume they're uncorrelated, beta 1 is going to represent the full relationship between x and y. Beta 2 is going to represent the full extent of the relationship between x2 and y. They don't fight against each other. They're unrelated. Each gets its own variance. If they are related, then the beta 1 that shows up when x1 is by itself is different than the beta 1 that shows up when paired with x2. Each of these betas is after controlling for. It represents the unique effect, whatever x1 has that x2 doesn't have, and vice versa. So hang on to that concept, and let's think about what these variables mean. So let's say that I have two different groups, two people from each of the two groups. So I have my original x, my level 1 x. This person has a 2, this person has a 4. That gives them a group mean of 3. This person has a 6, this person has an 8. That gives me a group mean of 7. Small groups, but it works. Keep it on the slide. If the mean of these group means is 5, that would be a lovely place to center my level 2 predictor. So I make my new group mean x as the mean of x minus 5. That's supposed to be a bar over there. Apparently the bar got lost at some point. So 3 minus 5 is minus 2, 7 minus 5 is 2. So regardless of what happens at level 1, this green predictor is what goes in at level 2. Now let's think about what happens at level 1 under each centering strategy. what we just did, group mean centering. The within group variable is your score minus the group's mean. So in this case, the information that's contained here is just relative. Like, this first person is 1 unit lower than the rest of their group, and so is this person, even though they have a different score. Within group information is entirely relative to the group mean. It is orthogonal to the group mean. But over here, if we don't group mean center, if we just pick a centering constant near the middle so that 0 means something, this column still contains group level 2 information. It's still smushed. So if you think about what happens in terms of unique effects, this column, grand mean centering, is related to group mean. They have to fight against each other. So what their effects mean changes based on whether the other is in the model. If you don't put group mean in the model, this grand mean centered level 1 predictor gives you the smushed effect. It has both level 2 variation and level 1 variation, so its one fixed effect has to do the work of 2. If we put the group mean in the model, and I'm changing the colors from a different green to an aqua to show you that it's going to mean something different. Let's think about unique effects. So level 1x has level 2 between group and level 1 within group information. Level 2x, the group mean, has only level 2. So what is unique about this purple level 1x predictor? What information is unique to it that the other predictor in the model doesn't have? The within level 1. So now the effect of level 1x has been unsmushed into the same within group effect we get in the group mean centered model. Here it happens through statistical parceling rather than making a new variable. So the unique effect of level 1x is the level 1 effect after controlling for the level 2 group mean variance. Okay, with me so far? No? Do you want to hear it again or hear it differently?
Yeah, say it again. What about the
Yeah.
partial?
Parcel.
Partial, right?
Now, not a parcel. Partially.
Partially.
Yeah. Not the voodoo parceling that, like, you know, you add items up and pretend like you didn't. Like, no, none of that. I mean like controlling for, right? Like a partial correlation or semi-partial, like that kind of partial. So, let's do it again. Level 1x. All you've done is subtract a constant. So you just moved it, right? Or left it alone, whatever. It still has level 1 variance and level 2 variance. Level 2x only has level 2 variance. It's the group mean. So what does level 1x have that group mean x doesn't in terms of its unique information? Level 1. The level 1 predictor has level 1 and level 2. The level 2 predictor only has level 2. So its level 1 unique effect is what its fixed effect becomes. The within group effect, the same that we got in the other model. We got it this way in the other model because we took all the level 2 variance out of the predictor to begin with. Now we're letting the model take out the level 2 variance by controlling for it as another predictor. The model is partialing it. I'm gonna need more caffeine. Parceling? Damn it. Taking it out. How's that?
I'm not going to try to help you.
You're not gonna help me?
For obvious reasons.
Yeah.
If you cannot pronounce it, I will not even attempt.
Partialing.
Partially.
Partialing. That just sounds weird to me, but I got it.
Is partially is right?
I think so.
I don't know.
It's related to the 0-1 binary.
Yeah. A 0-1 binary level 1 predictor still has level 2 variance in it to the extent that some groups have more ones. So if I just put in binary level 1x, binary level 1x still has level 2 variation in it. But I control for it by putting in the group mean, and so the level 1 predictor's unique effect becomes the level 1 effect.
If your level 1 predictor would be continuous or numerical, this will work in the same way.
Doesn't matter. Yeah. The idea is that this applies anytime you have a level 1 predictor that you have not taken the level 2 variance out of. Either it didn't have it to begin with, or you didn't take it out. Didn't have it to begin with happens very rarely. Question?
So I can do the same thing with other variables, so I don't have to create 2 variables.
Right, but we've been at this one parameter for like 15 minutes now, and I'm saying like the other way is easier because you haven't gotten to this one yet. So before, because this level 2 variable only had level 2 variance, it could only be the between group effect. But there's level 2 variance in this one too. So it has to work against it to get its unique effect. And the effect that it takes is something called the contextual effect. This is one of the hardest things that I've ever had to explain to people. I can't tell you how many questions I've gotten about this over the years. Chapter 8 in my book is like 1,000,000 pages long because of this. It's a hard concept. But we're going to get to it because in cluster data, this is probably 90% of what I see. People do it this way.
Isn't that it because it's easier to fit? Because people just create the mean variable and fit that in the model.
Well, there's only one more line of code to create your level 1 variable. So if it's easier, I don't think it is. I mean, that's not a reason.
Why do you think that people use this one?
Because the contextual effect is a different kind of level 2 effect. What it is the extra effect of the group after controlling for the individual. I'll say that again. The contextual effect is the extra effect of the group mean after controlling for the individual. So that's the easier way to think about it. Mathematically, the contextual effect is the difference between the between group effect and the within group effect. So you can think of it either way.
So this mu gamma 01 should be the difference between the level 1 and level 2 in the previous approach.
Yep. Wait for it. Here you go. Yes, because some of you want to see the math, and because I've had to defend myself against other people who tell me that within centering is weird and wrong, and I'm like, no, math don't care. These are linear combinations of E2. So the top model is a group mean centered model. The bottom model is the grand mean centered model. Both have the level 2 mean in as a level 2 main effect. If you work out the math, here's the equivalency. The fixed intercept is the same either way. The level 1 within group effect is the same either way after controlling for the level 2 mean in the grand mean centered model. What you get at level 2 depends on what's at level 1. So why this is so hella confusing? A different variable goes in at level 1 in each case. Even though it is a different variable, its fixed effect ends up being the same. Meanwhile, at level 2, the same variable goes in, but what its fixed effect ends up meaning differs. In the group mean centered model, group mean x, this is the between group effect. It's the effect of the group not controlling for the individual. In the grand mean centered model, the level 2 effect is the contextual effect. It's the effect of the group after controlling for the individual. It's also the difference of between and within effects. So regardless of which you choose, you can get to the other. So what you get directly in group mean centering is within and between. Between minus within is contextual. What you get directly using grand mean centering is within and contextual. You add them together, you get between.
Can you go back to the previous slide?
Yep,
So,
I got some pictures too.
yeah.
This one?
So there's a C1 and C2.
Constants.
So these two represent the same thing?
Could be, doesn't matter.
Doesn't matter?
Nope. It's convenient to pick the same constant to center at both levels. You don't have to, though.
Okay.
There are some people who pick the level 1 grand mean for this one and the level 2 grand mean for that one. Just changes what 0 means, but it doesn't matter. It doesn't have any consequence with respect to smushing or what these effects mean if you pick a constant. The big difference is if you pick a different variable. So group mean centering is centering at a variable. It is taking information out of this variable. Grand mean centering is just taking the information and shoving it over this way. Doesn't matter if you center or not. It still has two different kinds of information. So the only way to get a correct effect is to control for the other source of information in the model.
So within and between are two different variations. Why can you extract within from the between to get a different?
Say that again. I'm not sure I follow your question.
The contextual is the between minus within.
Yes.
To me, it's like you have two concepts, but they should not be related because you have the variation for between and the variation for within. So they don't interfere with each other. And now you're using one minus the other. What is the difference? What does the difference mean?
Okay, I got a picture. Where's my picture? There it is. Yeah. So this is sort of a diagram of what happens. So if you throw in the group mean at level 2, it has a contextual effect. The original variable at level 1, the level 2 part of it still has an effect at level 2. So contextual just fills in the gap to get to what the total between group effect should be. If you don't like that, maybe you like this one. So this is student reading on the x-axis, student math on the y-axis, okay? These are 3 different lines for 3 different schools. School mean reading 4 is red, blue is 6, and green is 5, okay? On the x-axis is original student reading, okay? So if I am an average student, to know what that score translates to, I have to know which school I'm in. An average student at the blue school gets a 6. An average student at the green school gets a 5, and so on. The slope through the school means the yellow line, that's the between effect at level 2. That's what group mean centering gives you at level 2 directly. The slope of the individual lines, the impact of being relatively higher or lower than everyone else in your school, that's the level 1 within school effect that either model gives you once you have the level 2 mean included. The contextual effect is the idea of the incremental effect of the school after controlling for the individual. So to control for the individual, I got to nail them down to a value, like 5. So after I control for the fact that a given student has a 5, what else affects their score about their school? It is the difference along this vertical line that is the contextual effect. For every unit higher mean reading, the whole school's effect, language, whatever, damn it, math, is supposed to be higher by 1.5. So the contextual effect is anchored to talk about like what happens after I deal with the fact that you have a 5. The between school effect is not anchored in that same way. So the between school effect is the effect of the group. The contextual level 2 effect is the effect of the group after controlling for the person.
So means so I think still kind of confused. But so you said like many people do like actually like a contextual effect like,
Yes.
without thinking group mean.
Yes.
So then it's a reason like why people often explain like multiplicative like a fixed effect is like simply like how the like a slope like moves to like vertical.
Uh-huh. Yeah, I mean, it's hard to think of a slope of a vertical line, but that's kind of what it means. It's this shift in intercept at the same point on
At the
x.
same point.
At the same point.
But for group means like centering like it's like yellow line.
It's the yellow line, yeah.
Oh,
That's the difference.
that's
So for longitudinal data, I'm all about the yellow. Because that is people and occasions, and there's no such thing as like controlling for an occasion, because occasions aren't entities. But for cluster data, like what if I said, reading is good for you? Well, duh. So that's why I read lots and lots to my kid. Now, after I control for the fact that I read a lot to my kid, is it good that I send him to a school where other parents are doing lots of reading too? Does that help extra? If it does, there's a contextual effect. And so a lot of clustered data hypotheses are phrased in that, what is the extra impact of your environment after you control for your own characteristics? The contextual effect directly answers that question. So the between effect is level 2, not controlling for level 1. The contextual effect is level 2 after controlling for level 1.
So it means when you use group mean like the coefficient would be like 1.5, or like when you use a group mean like it's gonna be 2.
Yeah,
No, it's reading. Sorry, like
the slope of the yellow is 2. The slope of the individual lines for within is 0.5. The difference between 2 and 0.5 is 1.5, which is the contextual shift per unit school mean.
Yeah. But in the case of group mean, it's going to be actually 2 because like the mean of like each school like has a
Yes.
like 2 points difference.
Yes. The yellow line slope is 2. The individual line slope is 1, and the difference between, 0.5, and the difference between the yellow and each is 1.5, which is the shift on this y-axis.
It's a reason why you say conditional. Okay, got it.
Hey, well, I'm glad I pleased someone today. So the other way to think about this contextual effect is if going to a school with more reading didn't matter after controlling for your own reading, all of these things would be flat on top of each other. There would just be one slope going through the data, like red and green and blue would just all overlap. That's what it would mean if the between effect and the within effect are the same. And that's what the smushed effect gives you without testing for it. So the other way to think about the contextual effect is as your formal test of smushing. If the between and within effects are the same, their difference will be 0. Contextual effect will be 0.
I have a question that's not immediately related to this. Even if you're including things like controls, like say you're not actually interested in this part of the research question, you just have a lot of controls, do you still need to like unsmush them?
Yes, always. And guess what happens if this were students in classes in schools? Yeah, we're done. 3-level smushing. So, yeah, I know. That's a fun part to leave on. How about that? So, all right, kids. We'll have to save the rest of this exciting conclusion for next time. I'll show you an example. Doing it this way so you get practice with that. Office hours start now. Let me know if you need anything. So, thank you.